All right. So I guess we're now live. So hey everyone, thanks so much for joining us. We're really excited to have you for the latest installment of Data Science in 30 Minutes. So we're just going to hang out here and start momentarily. I think we're seeing that people are slowly trickling in, and we want to give folks time to make it in. So we're just going to sort of sit here, sit tight, and we'll start momentarily. In the meantime, actually, for those of you who have joined us and want to be able to follow along, I think if you look at your YouTube chats or the sort of comments in the YouTube section, you'll see that there are links for both the presentation that my friend Ian here is going to be sharing, as well as a link to the GitHub account. So you might want to download those and start playing around with them. All right, so it's about 5:30. So for those of you who are joining us, congratulations. We're really excited to have you. I'm Michael, the founder of the Data Incubator. So we run a free fellowship for PhDs and master students. And if you're interested, you can apply online at thedataincubator.com. We also, of course, do corporate training. So if you're interested in having your firm do some data science corporate training, you can sign up at thedataincubator.com as well. So today we're going to be talking, we're going to be doing another installment of Data Science in 30 Minutes, or the ES30 as we call it. We've done, we've had a number of interesting and exciting guests, from Becky Tucker, who was a data scientist at Netflix, to Jess Stolf, who was VP of Data at Quantopian, and Sam Swift, who was VP of Data Science at Betterment, and also a former fellow at the Data Incubator. And so today we're really excited to be joined by another former alum, Ian. Wave, say hi to everyone, Ian.
Hi.
So Ian will be talking about the connection between science and data science, and how his training as a scientist helped him prepare for his career as data science, and how that can kind of give back to science. Ian got his PhD from the University of Edinburgh, and he was a TDI fellow, a Data Incubator fellow, in 2015. So he's now the VP of Science at Cerego, and as I mentioned, he's also a former fellow, so we're really excited to have him. So without further ado, Ian, do you want to take it away?
Certainly. Thank you very much for that kind introduction, Michael. I'm just going to share my screen here and get onto these slides. Is that working?
Yep, that looks good.
Okay. So as I think Mike said, I have the links to both this slide deck and also the sort of GitHub repo where I've put a little bit of sample data in there. So if you want to follow along with this, you can, if the connection's not good enough. And also there are some links at the end of this as well you might want to explore. Okay, so I'm going to be talking about how we combine cognitive science with machine learning at the company that I work for. Basically, the thing that I found interesting about data science, the thing that I've really learned about it since I started working here, is that domain expertise really is incredibly valuable. And scientific thinking is also a hugely valuable toolkit. I think it's really the set of things that will make you valuable above standard sort of machine learning out-of-the-box techniques in the industry. Really the ability to interpret the data that you're working with to a very deep degree. So I'm going to talk specifically about the field that we work in, which is cognitive science and learning science in particular, and how that sort of guided the development of our prediction algorithms, and how the predictions in turn that they output our understanding of cognitive science. So we're not, a household name like Netflix or Betterment, so I'll give you guys a quick overview of who we are and what we do at Cerego. So Michael's already told you I'm VP of Science at Cerego, and I was a fellow at the Data Incubator about 1.5 years ago. And it took me a couple of tries to gain entry to the fellowship program, so that's definitely don't give up, it's worth it. His background is in neuroinformatics, with a particular focus on human memory. So that's really a sort of neuroscience, cognitive science focus, did some brain imaging, but for people with a math background in my case, and in other cases physics and computer science background. So pretty good training for data science, in particular the science side of things. Cerego are a small company that punch above their weight. We are about 25 of us just now. That's about double what it was when I started. We're headquartered in San Francisco, so we also have an office in Japan, and our partners are worldwide. We're a learning and training platform. We work with other companies. We're B2B, business to business. So we see ourselves where our partners are they have the what of learning. They know what they learn, whether that's some content for a course or whether it's some training, whatever they want them to learn. We're really the how of learning. So we help people learn and retain that information. So some of our partners are listed here. This is slightly out of date, but we have partners in roughly 4 big categories. So publishing, we have a lot of large publishers we work with, like Cengage and Elsevier. We have partnerships with several charitable organizations. So Bill and Melinda Gates Foundation we work with, and the Queen Rania Foundation in Jordan. Some educational institutions, as you might expect, and also quite a lot of corporate training. And overall, you could describe Cerego as being a generalizable, personalized learning platform. So what we mean by that is you should be able to learn anything with Cerego. We put a lot of effort into creating item types that you can learn anything from. And it's also personalized. That's really important. So the schedule that you get and the sort of learning experience that you get is going to be optimized for you. We'll talk a little bit about that. And that's the specific problem I'll talk about today. How do we actually do that? That requires quite a lot of prediction. And our overall mission, which we feel very deeply, is to help people acquire and measure their knowledge, right? So to know what they know and capability. And so you can think of our platform as being structured of roughly 4 components, 3 of which I have a pretty heavy input into these days as the sort of head of the science department. Content is one of those. That's the what of what you learn and how you structure that in the system, how we get it into the system. The delivery of the content, right? So that's a very technical task. Cerego, because we work with a lot of different partners, has to embed in all sorts of different situations, or you'd be used as a standalone tool, be accessible for everybody. Learning, that's obviously a big focus for us. That's something we'll be talking about today, which is scheduling things in a way that you learn things most effectively and retain that information for longer. And then insights, which is very, very important, right? So we don't just help people learn, we also show them what they know and how well they know it. So I'll take you through a little bit of background in learning science, which is the field that we work in. It's a sub-area of cognitive science. And as a learning science related company, I'm legally obliged to show you this Ebbinghaus slide. So he is thought of in many ways as being the grandfather of the field of learning science. And the reason for this is he's one of the first people to really take an interest in measuring his memory in a quantitative way, right? So this gentleman here around the turn of the 20th century, beginning of the 20th century, at the end of the 19th century, started teaching himself various little, usually nonsense syllables and nonsense facts, and measured how long it took those things to decay from memory, and noted that memories always decayed if you didn't go back and review them. And he also mapped out what that decay curve looked like, and that's something that's been very influential. Really, in my sort of time in the sort of science, the most interesting period I think is really the 60s to 90s, 1960s to 1990s. That's really the point where we had a sort of cognitive science revolution, where we started to combine psychology and neuroscience in a meaningful way and started to understand some of the factors that affect the rate of that decay and the shape of that memory decay curve, right? So affects how long you can retain information for. A couple of the big things that came out of that are really important, amongst many, many other things, are something called the testing effect. So this is a phenomenon where if you test yourself on some material instead of rereading it or restudying it, you get a much bigger boost to your future retention for that material. So you even if you get it wrong, if you're actively engaging in trying to retrieve and recall that information, you're building these much more robust memories for that material that will last longer into the future. That's very effective. Effective and well-known technique is spaced rehearsal. So that's where, rather than studying in one block, you come back to and review the same item several times over a long period of time. Usually there's a sort of expanding interval of time between each review. And that also leads to much stronger memory, much better retention for that material than if you just sat down and reviewed it at once. And together, these two things actually can sort of be thought of as one problem, right? Which is trying to reach something called desirable difficulty when you review some material. And so desirable difficulty can be defined as that sort of optimal moment for learning, which is when a memory is faded to the extent that it is hard but not completely impossible to retrieve. And that maximizes your engagement. It builds this very robust memory that lasts for a long period of time. And so desirable difficulty is really something that we're aiming to reach when we're learning. And that leads to a very direct problem to solve, which is how do you schedule these reviews, these spaced rehearsals, to hit that optimal moment, right? And so to do that, you need to know when people are going to hit that desirable difficulty, when it's going to be just hard enough that they really have to engage, but they've still got a chance of getting that question right. And this is a classic prediction problem. So it's exactly the sort of thing that data science is really being developed to solve. So often when people talk about scheduling and spaced rehearsal, and they talk about Ebbinghaus and the forgetting curve, they'll present an image something like this sort of one-dimensional curve, right? It's actually an awful lot more complicated than that, which you can start to see as you map out some of the different dimensions. This is a very one-dimensional slice of a very multi-dimensional problem. So one obvious thing is, this is some data that we have from our system on how the decay curves look after different numbers of reviews that you've done within the system. So the bottom curve, the gray curve, is when you've just come in as material, what your memory for that looks like afterwards if you haven't reviewed it in the interim. And it decays, from somewhere around 80% to around 60%. After you've come in and done one review in Cerego, you can see the decay curve is not just pushed upwards because you know it better, but it's also shallower, right? It decays more slowly, and so on and so forth as you do your second and third and fourth review within the system. You start to approach a point where the memory for that material is really robust and really sort of mastered to this kind of ceiling level of around about 90% here. So that even 6 weeks later, you've got very similar memory for this material than when you last looked at it. And this is data from 7,500 learners in our system. It's around 16 million reviews to build these curves. But it's also only showing you one little snapshot. So it's lumping together all of the different sort of past histories that people have with these, except for the number of reviews that they've done. So one person could have come in and been correct 3 times. One person could have done all of those 3 reviews in a previous day, and one person could have taken a year to do those previous 3 reviews. So people in academia have tried also to map out this problem. Here's an example from a paper which I linked to at the end of this presentation. This is something called the temporal. Well, I can't even remember the optimal temporal ridgeline which basically relates the amount of time you wait between study and your initial review. And the length of time that memory will last after that first review. So you can see that already that's working out into a 2-dimensional problem. This took an academic group, well over 1,000 participants, and those are actual physical people that they have to get into the lab and do the work, and they have to track over the course of a year in order to map out these memories. And all of this is in aid just of learning about this first review. So really this sort of 2-dimensional, 3-dimensional surface corresponds to the one review curve in that plot that I showed you to the left. So hopefully I'm giving you a sense of how complex the problem actually starts to be when you realize that the thing that determines how well you can retain some information is your past history with that item, right? When you've come in a review, the gap between those reviews, your success or otherwise in those reviews, what you've done, how deeply you've engaged in those. And then you get this sort of forking tree where there are lots of different past histories. that together should help you to predict what somebody's memory decay curve should look like today. And so that's the problem we're trying to solve, right? Given some past history with the data, what can we say about what their memory decay curve is going to look like, and therefore how accurate they're going to be at a given point in the future. And I've given a sample data set, and again, this is linked at the end of this deck. It's also linked, I think, in the actual YouTube page. I've uploaded a sample deck, and I've gone into a fair bit of detail about the kinds of things you might want to think about. So you can go in and sort of play around with that and tackle this as a data science problem. I think it's a really nice problem to play with. The reason I say that is that it's got a very simple sounding definition, right? We want to predict how accurate somebody is going to be at a given moment in time, given their history with an item being learned. It also sits at the sort of intersection of data science and academic science. And so it's something that is very tightly constrained by science, right? So it's something that we've studied a lot, and there are very specific shapes of curves. And I go into a little bit of detail here. So for example, you can try out different types of decay curves, exponential decays, power decays. There's quite a lot of research on what actually is valid. But it also requires a lot of data in order to map out this space, in order to test it properly. So it's also quite a large data problem. It also highlights a trade-off between accuracy and interpretability, which is often a trade-off whether you sort of realize it or not when you're doing data science, which is that you can make an incredibly accurate model, or you can make a model that's very interpretable, that has sort of a small number of parameters that have a clear meaning in real life. And really, the sort of approach that you take, whether you aim for accuracy or interpretability, is really dependent on who your audience is, right? And what the problem is that you're actually trying to solve. And so this is where it also sits at the intersection of science and industry, in that in industry, you have to be incredibly aware of what the problem is and what the audience is. And so, for example, if you're trying to come up with just a specific moment in time to bring a learner back to review some material, you don't necessarily need your data to be particularly interpretable. You want it to be very accurate. But if you're trying to tell the learner how well they know something, you've got to give them something interpretable that they understand. Or if you want to generalize this to another group of learners, the same applies. So the primary aim of this would be to try and predict the likely accuracy of a test of a given type, so multiple types of tests in the system for a given user at a given future moment in time. Solving this problem is super important for this kind of problem, for being able to learn effectively, because it allows you then, because you have the memory decay curve for all of the different memories that are being learned in the system, you can pick the optimal time for people to come back and review, because you know at what point they're going to hit this desirable difficulty. And so you can notify someone to come back in and give them just the 10 items that are just reaching that difficulty, and help them learn that and build retention very effectively. There's a more challenging aim as well, though, which is to try and summarize the learning, for example, of a given user, right? To be able to come up with a metric or 2 metrics or 3 metrics that really tell you something about that person, how well they're performing, whether they're struggling. You could tell something about a particular item, how difficult it is. And that's where you want to lean more towards the interpretability, and you might take more of a scientifically constrained and structured model to do so. So this is an example, and I've also included this in the GitHub repo. This is an example of a fairly simple but relatively well-calibrated model built on the type of data in the sample. So this is showing the calibration. So this is showing the actual outcome of a trial as a function of its predicted outcome from the model. So this is actually trained on more trials. It's tested on about 4 million trials. And you can see that it's pretty well calibrated, right? It stays close to that dotted line, which would be a perfectly calibrated model. But there is some deviation. Most of that deviation occurs in a part of the space where you don't have many trials. So most of the trials in our system are pretty well learned, and you have an average accuracy of somewhere around 0.8, 0.85. And that means that most of the trials land in this upper right corner, where we're reasonably well calibrated, where we're north of 60% predicted accuracy. But even still, there's clearly this phenomenon where our predictive model, which hews very closely to the science, is slightly conservative at lower accuracy. There's a question as to why that might be the case. Well, if you think about it, the models that we're using and the models that we're constraining it to are the ones that have a lot of scientific evidence for them. So in this case, we're using a power decay curve. And there's very good reason to think that that should be the way that individual memories decay over time. But it's clearly a little bit conservative when it comes to these memories that have not been seen for a very long time and that we're predicting low probability of accuracy for as a result. And the reason for that might be that this is real world data, right, rather than a lab. So in this case, unlike in a lab, these are things that people are actually trying to learn. They might be something related to a course, they might be the sort of thing they're encountering regularly outside of our system. And so one of the reasons why you might expect some conservative estimate from something like this is that actually they're getting more interaction than the system knows about outside of it. So that's a little aside and something else that sort of highlights the difference between the kind of very large real-world data sets that we have and the sort of pure lab data, I guess, that some of these models have been derived from. And it's one reason why you might want to stick more closely to the sort of science and the very evidence-backed science in a lot of ways, because if you just did a straight prediction on this real-world data, it might not generalize very well, because the phenomenon that you see here that pulls this curve away might be a little bit different in a different system or a different context. So one reason why it's useful to have an extremely accurate model is not so much that you want to predict down to the nearest minute when you should bring somebody else back into the system to learn. People have, busy schedules, and it's not realistic to expect people to turn up at the exact second that your models predicted them to, so that you end up getting kind of diminishing returns for making a more and more precise, more and more accurate model when it comes to the end user, when it comes to learning. Where it does become incredibly useful is the second part of what Cerego does, which is showing you what you know. And we use this metric a lot in our internal, we use this sort of model a lot in our internal research. What I mean by that is, if you have a very strong sense of, a pretty accurate, well-calibrated sense of how accurate somebody should be on a given trial, given the sort of main things you know about that and the main factors that affect that, how long ago they saw the material, how well learned it was before, then when you have deviations from that, you're able to spot that, right? You can factor out those big things and you can start to understand, okay, when they exhibit this particular behavior, or when they do this during a trial, we actually see an improvement relative to what we would expect in terms of their learning. And so we spend quite a lot of time doing that with the platform. So in other words, by knowing how memory should behave, we're able to measure when something improves it or makes it worse. And in practice, because we're a learning company, our mission is to help people learn better and learn faster, rather than spending all of our time just fine-tuning this model in order to get them back at a certain moment in time. We can actually use the model to go back and look at the cognitive science a little bit more, right? Approach it like scientists, see manipulation and see what effect that has. I'll give you a few examples of how we do that. So one of these examples is session size, right? So with the timestamps in the sample data they've given you, you can also look at this. You can start to bunch things into sessions and see how long a user's staying in the system and doing work for a specific, in a specific bunch of time. When we look at this over time, right, the circles in this plot are the number of users. So you can see most of our users have a session size of somewhere between 50 and 100 trials, right? So they come in, they do maybe 50 to 100 reviews at a time. What we find is on the y-axis, we show how effective the user is at actually learning that material that they're trying to learn. This is the sort of thing then that we have this predictive model and we can look at deviations from it. What we noticed was that it was actually relatively inefficient to come in for that length of time. You've got these diminishing returns. There's lots of reasons for that: fatigue, priming effects, and so on. And there's a kind of sweet spot of the amount of material you should learn in any one go before you go off and have a break. And it's somewhere around 25, right? It's somewhere in that kind of area. And so we've reconfigured our interface to encourage learning chunks of roughly that length of time. So that's something that's had a practical impact on how we help people learn. Something else that we can look at is how effective you are at different times of day. So this data is from our beloved CEO, Andrew Smith-Lewis. He studies on Cerego a lot. He's very smart. He has thousands and thousands of memories. And this pie chart shows you around the 24-hour clock when he does most of his studying. And he studies most of his time in the morning, before and just after noon. But actually, it's colored by when he is most efficient at building retention, most efficient at learning. And you'll see from this that actually we found he's far more efficient at learning. He builds more retention for the memories that he studies just before he goes to bed, right? Just before he sleeps, which is interesting, right? That's something that, again, you might look at the cognitive science and say it's something you might expect as a hypothesis if sleep consolidation has a big effect on how much you're able to retain. So it's an interesting pattern to see from that. It's the sort of thing, again, that you can help learners with. You can tell them to come back into the system at a particular time because it's more beneficial for them to try and learn then than earlier in the day. This is a slightly complex but a really kind of interesting phenomenon. So we have a screen before you're able to answer in Cerego. So you come in, you see what the question is going to be, and then you're given an opportunity to kind of pause and think about the question, really engage with it, and try and retrieve it from memory, right? Which we know is something that should be beneficial. And then you hit a button and you maybe get some options, or you type it in, you try and answer the question. What we see is that the longer you take on that trial, the less likely you are to be right. Okay, so it's sort of a measure of confidence. If you hit the button and go straight to answer it, usually you're getting it right. It's usually because you're confident. We find the reverse effect, though, for your following reviews in the future. In other words, how much you've actually learned and how much retention you've built. We find you're actually comparatively more effective in the future if you've taken longer on that earlier trial to actually engage with the material. And that happens regardless of whether you end up getting that early trial correct or incorrect. And then we also look at other behavioral factors. So for example, we wanted to check whether people who used our mobile app were learning as effectively. We found they did a lot more practice, right, which makes sense. The mobile app is just more available. It's there. Even though they have the same amount of material to learn, they tended to do twice as many reviews in the system. We also found it changed how they reviewed. So they started to review in smaller chunks. So they started to do fewer reviews per session, did more than twice as many sessions. And they also tended to come back to the system more frequently, which meant they were doing more of their reviews in the kind of ideal schedule that Cerego was providing to them. So they were getting to their reviews as they were hitting that desirable difficulty relative to the people who just used the desktop and the web app. And as a result, we found that they actually learned significantly more effectively. So it wasn't just that they were doing more in the system, but they were actually learning more from the experience. They were actually building their memory retention faster than people who were just using the web app. So hopefully that's a very quick sort of high-level summary of the kind of problem that we've been looking at and how that relates to the cognitive science that we come from and the data science that you apply to it. As I mentioned, there's a set of resources here that you might want to check out if you want to go to that link. So you can try Cerego itself. So there's a little example course so you can see. It's always a lot easier to see and understand the kind of thing you have a chance to delve into it and try it out. That's something I definitely encourage you to do if you want to also go and play with the data. It's having some relatively deep understanding of the system you're trying to model is very, very important. You can also read our white paper if you're interested in a lot more detail of this kind of thing, or our blog where we post sort of some of these things that I showed you about the learning factors. If you're interested in how learning science in practice actually works, in particular how effective it is for in-class techniques and things, there's an excellent review by John Dunlosky and some colleagues from 2013. I've linked to that there. It's very readable. It's very applied. It's an excellent review of how effective these various techniques are, relatively speaking. We've also got a couple of really interesting South by Southwest talk from our CEO, Andrew Smith-Lewis, and a blog post from my colleague, Kit Rickett, on why retention itself is important and how it relates to creativity. This is the GitHub repo that I've been talking about. It's also linked in the YouTube thing. And then if you want a deeper dive into some of the science, that's also available there. Okay.
Cool. Thank you so much, Ian. I'd love to just pick your brain a little bit about how you think your experience as a PhD has helped inform the work you're now doing at Cerego as a data scientist.
Yeah, so my PhD was very focused on human memory, and so it's got a very, very direct link to what I'm doing here. I think there's two ways. There's obviously that specific expertise, right? So I kind of, with certain ideas, I know kind of where to look in the literature for various things. That's all interesting in and of itself. Maybe the bigger thing, though, is the general practice of understanding that almost any system you're working with is much more complex than it first appears. And that there's almost always several different confounds that you just didn't anticipate when you first model a problem. And so I find what tends to happen is that I have an initial pass at trying to solve a problem, sort of high-level view, and it'll look really interesting. And maybe at that point, you get a result that looks super interesting. In academia, it looks like really publishable. And then you'll give it a couple of days, and you'll come back to it, and you'll think, oh wait, hang on, actually that's because I'm accidentally selecting out a certain subset of users that have maybe this characteristic. So you start to control for that confound, and then you control another confound. And I think it's a good measure of how good you are as a scientist, and particularly how good you are as a data scientist, is how far down that path you can go. Because that's where you're really getting to kind of the truth and the nub of the specific question you're trying to ask. So that's probably the most helpful thing, I think, most helpful skill that I learned, sort of refined in the Data Incubator and in my job here.
Oh, wonderful. And then let's do the reverse question. How do you think what you learned at the Data Incubator, or as a scientist, or as a data scientist, practicing data scientist now, has maybe informed, is not quite the right word, but has made you sort of go back and said, wow, if I were still in the academic field, I would have approached this problem this way, or I would have used this tool and this other problem?
Absolutely. And in this specific field, actually, it's huge. So I didn't go into too much detail with it in this talk, but a lot of the time when we sort of bring up Hermann Ebbinghaus as this kind of iconic thinker, and we bring up Robert Bjork, some of the other iconic figures of the 60s and 90s, we're all working with incredibly small data sets, right? We're all doing so very, very smartly in order to strip out these confounds and answer these questions. But you start getting to these problems, like, when you should schedule things and sort of relatively small effects on memory that are actually meaningful when you're trying to understand something about the neuroscience. You can't answer without having a lot of data. You can't answer without knowing how to work through that data and strip out those confounds and so on and so forth. And so there's sort of, in many ways, you can sort of look at Hermann Ebbinghaus's era as being a golden age for psychological science and learning science, and that's the birth of really the systematic quantification of it. In the 60s and 90s, when it starts to interact very directly with neuroscience, and you start to understand much more about what the brain is doing. And then there's sort of this new golden age that I really think is underway. And we work directly, actually, with researchers where we share our data, and they use it. And there's lots of other groups doing that kind of thing too. So we work directly with the University of Toronto, for example. And it's this ability to, now we have access to these very large longitudinal data sets. So what I mean by that is learning that's happening in the real world over a long period of time, over months and years, where you can really study in detail and fine detail how memories are changing over time. You've got enough data to do that. That's just simply something that's just has been impractical to get, but I'd love to have had access to while I was doing my PhD.
Yeah.
Yeah, and that's one really obvious practical way in which data science is really helping that field.
Yeah, I mean, I think that's actually one of the major themes around data science, right? It's, in many ways, it's sort of tools and techniques that become necessary or useful once you are in a world where you suddenly have, where data quantity is no longer constrained. And there's sort of kind of a mindset shift almost from an academic world where data is sort of purposely collected and therefore necessarily small because of constrained budgets, to now we have a mobile app which people are using for free, and we have more data than we know how to store. And how do you think about taking advantage of that data? And I think that, that kind of mindset shift is certainly a very big one that we've seen in the data science community. And I think that you see with our fellows as they're trying to make that transition from academia into data science.
Yeah.
And speaking of confounding factors, I think it's Jonathan Reed asked, how do you take into account users who are casually engaging with the material? For example, someone who's multitasking, switching between Facebook, their cell phone, preparing food, etc., and how that affects their time per question?
Yeah, so so that would be specifically for the question on recall. Well, so the obvious answer to that is that the predictive model that we have takes the user into account separately as a specific factor, right? So each user will have their own kind of decay curves that we expect. So effectively, all the analyses we're doing are within user. So then the problem becomes, okay, so the user perhaps today is not paying attention, but on the previous day isn't. I suppose that's sort of there's less variability there than the variability you see between users, so we sort of control for it a little bit in that way. But again, I mean, this is sort of, again, related to what you were just saying about data science and the kind of new things that you have to take into account is that's an excellent example where you have all this data, you're no longer constrained so much by data quality, data quantity, if at all, but you are very constrained by data quality. And it becomes more and more important to think about these kinds of questions about data and how do I strip things out afterwards and things like that. So, for example, you know, when I'm dealing with things like recall data, you take the logs, maybe you strip out some patterns that look like people aren't paying attention. We certainly do see that from time to time in the data. That's
Yes. Okay. No, makes a lot of sense. And another question from Tillman Net: could the increase in effectiveness of your CEO, right, during that kind of midnight time period, could that just be attributed to the fact that he's spending less time learning during that time period, and therefore sort of just diminishing returns, right?
That's really interesting. Yeah, it might be that you find that when people are, maybe that's the time when it's just clearing out a very small session size. Do you know what I think is actually happening in that plot? I suspect what he's doing in the sort of morning period and during the day is he's demoing the product a lot. And so he's probably deliberately getting a few things wrong just to show people how the system works, and that's messing up his data. So in his specific case, you know, again, this is another example where you need to be an expertise in the domain, expertise in the system, and I'm a little bit of an expert in the way that our CEO demos the product, so I've got a sense of, you know, what the confounds might be. So hit that not to a journal necessarily and claim that it shows memory consolidation during sleep. But,
that's a great story.
Yeah.
So one last question. So you were obviously a fellow at the Data Incubator a little while ago. What do you think you learned as a fellow that was most useful for your current role at Cerego?
You know, I came into the Data Incubator, I think I mentioned this at the start. It took me a couple of goes to get in. And that's partly because I came from, you know, I did pure math originally, but then I was in a science that wasn't quite as sort of, I didn't have quite as many sort of programming skills as a lot of the applicants. So that's definitely one area. I think just the breadth of exposure you get to different approaches, right? So to different tools that you might need. So it's a very compressed 6 to 8 weeks. A lot of that time is interacting with people and working through problems. And anyone who's starting the Data Incubator at any point, that's absolutely where you should be spending your time, is talking to other people and working through things together. That's the most valuable thing. But even in that short space, it was kind of amazing how many different techniques we had introduced to us, and how much of a sense we got of the breadth of what you can do, and the number of different tools you have to apply to these kind of problems these days. So that's probably the thing that was most useful and most kind of surprising to me.
Oh, that's a really interesting take. And since you did mention you had multiple attempts, I'm sure many of the folks who are listening might be interested in what advice would you give them as they're applying?
I would say really it comes down to, if you're just trying to get into the Data Incubator, my suggestion would be to find as interesting a data set as you possibly can. Try and find something a bit unusual. Try and find something that's big, that requires you to use some sort of slightly novel techniques and things like that. You can get sort of nice, clean Yelp review data sets, and if you're really smart, then you'll probably manage to turn that into an interesting project. But having gone back to the Data Incubator, the projects that have always caught my eye are the ones where people have done something that no one else in that cohort has really thought of. That's been a little bit out there and a little bit out to the side. I think that's sort of a more interesting. I think in any case, you have to be very, very passionate about what you're doing. You've got to put a lot of hours into. You've obviously got to put a lot of hours into it once you're accepted. You must spend the month before and spend those 8 weeks really just doing this one thing day in, day out. And you've got to also spend a ton of time on the application. So it's got to be something you find interesting. It's got to be something you enjoy. You've got to come out of it. Maybe you didn't get in this time, but you've got to start a project that you really value and found enjoyable to do.
Cool. No, thank you. So I think that'll about wrap it up. This is Iain, who is the VP or the Vice President of Science at Cerego. And he was also a former Data Incubator Fellow, talking about cognitive science and data science. For those of you who are interested in our free fellowship for PhDs and master's students, you can apply online at www.dataincubator.com. If you're interested in hiring fellows, you can also find out more about hiring our fellows from our website, dataincubator.com, and you just go to hiring. And if you're interested in corporate training, we also offer that at our website again, and then you just click on training. So thank you, everyone, and thank you so much for joining us. Cheers.
Thanks.